Uh, the variable here is z. You can think of this px z over qz as a function fz. Yeah, this is the random variable. You can think of x as a constant, because now you care about is z, so you don't care about x. Yes. So in this, in this definition, the random variable is z. So you can think of x as a constant. Okay. So given this, next we are going to apply the Jason's inequality. I'm not sure in the convex optimization recitation, did you cover Jason's inequality? No. So basically, what Jason's inequality says is that if we have a function f, which is concave, you cover the convex and concave function, right? No. Okay. So we have a function f, which is concave. What Jason's inequality says is that if we take the expectation of x and evaluate it at f, this function value will greater or equal to the expectation of fx. So here is an example, which is this is a log function, which is concave. And we have 2 points here, x1 and x2. So the expectation of x1 and x2 must be some point in this line segment from x1 to x2, right? So the expectation of ex could be here, here, here. So let's say it's here. This is ex. And we have fx1 and fx2. This term here, we take the expectation of the fx values. This will give us a line connecting so the expectation of fx must be some point in this segment, fx1 to f in this segment, this one. So what Jason's inequality says is that fex1, which is here, fex, this value must be larger or equal to this value. It's kind of messy here. This is expectation of fx. So intuitively, if you take 2 points and connect their function values with a line, this is the chord of this function. Jason's inequality says that the graph of this function is always above this card. See, no matter how you draw these 2 points, the graph of this function is always above this chord. Let's take another example. You can think of f(ex) as the graph of this function, and the expectation of fx as the chord connecting these 2 points. And the function graph is always above this chord, as if the function is concave. Any questions here? So applying this Jason's inequality, we can get a lower bound of this guy. Because log function is concave, so according to Jason's inequality, this one becomes expectation of log pxc qz. Any questions about this step to this step? Okay. Now we can use the log function to factorize this ratio. So it will become expectation of q log pxz minus expectation of log qz, using the property of log function. Here is a ratio here, so the subtraction here. And this guy now becomes a lower bound of the original log likelihood. Now we want to ask, under what condition this equality here holds. If the equality here holds, which means that the log likelihood is equal to this lower bound. So in that case, instead of maximizing that guy, we can maximize this lower bound. The answer is, if we choose Q as QZ as the posterior of Z given X, these two things will become the same. So here we reach the conclusion of EM algorithm. If we choose the distribution QZ as the posterior of Z given X, the log likelihood of Pi, the log likelihood of X is the same as the lower bound. So in this case, we can operate over this lower bound, and all the process will be the same, because these two guys are equal to each other. From the very beginning, we choose arbitrary QZ.
And why are we concluding that QZ is equal to P?
You can plug in QZ into the lower bound, and it will give you the log likelihood. We can do it here. So if we choose QZ as this posterior, let's plug in this posterior into the lower bound. This will becomes sum over okay. Let's plug QZ equals to PZ given X into this lower bound. It will becomes sum over Z PZX log PXZ minus PZ given X log PZ given X. This is the definition of the expectation, right? We put these two terms together into this sum. This is log PXZ over PZX. And this term here is log PX, right? And the summation is over Z, so you can take log PX out. Log PX Z PZ given X. And this term is 1. So finally we get log PX. So we plug in the QZ equals to PZ given X into the lower bound. We found that the lower bound is equal to log PX. So given this conclusion, here is the EM algorithm. We iterate until some condition is met. So in the first step, I'm going to estimate PZ given X. After I get the value of this distribution, I plug in PZ given X into the lower bound and maximize it. So plug in QZ equals to PZ given X into this lower bound. And do the maximization. Because we know if QZ equals to PZ given X, the lower bound is equal to PX. So this step will guarantee you that you are still maximizing exactly the log likelihood, your original objective function. So we iterate between these two steps. Why we need an iterate here? Because when you are estimating PZ given X, you need the value of the global parameters. And to do the second step, you need an estimation of PZ given X. So the first step is called expectation, and then the second step is called maximization. In the first step, we estimate this distribution. Why it is called expectation? Actually, in the second step, we are using the expectation of this distribution. But since this is a multinomial, so the probability is the same as its expectation. And then in the second step, we are maximizing the lower bound. So that's why it's called EM algorithm. Let's first do the E step, which is to estimate P Z given X. This is very simple. It is PZX over PX. This is definition of conditional probability, right? And we factorize the joint probability into Px given Z, Pz, and Px. Now we take a value because they can take capital K values. We take an arbitrary value Z equals to small k x, and plug in Z equals to small k into this this equation. X Z equals to small k, P Z equals to small k, and Px. And this part is a Gaussian distribution, Nx mu k sigma k. Z equals to k means we assume X from the case cluster. So this probability is this guy. This density is this guy, and the P Z equals to k is pi k, the prior probability of choosing cluster k, and the Px is k equals pi k x mu k. Sorry, I should use another. J equals to 1 to capital K, pi j x mu j sigma j. This is a closed form solution of the posterior of Z. So you do all of this computation for Z equals to 1, Z equals to 1, Z equals 2 to capital K, and we'll give you the posterior, which is multinomial. Look at here. When you are trying to compute this posterior, you need the parameters pi k, mu k, sigma k, and all the parameters here, pi j, mu j, and sigma j. J runs from 1 to capital K. So that's why I said to do the E step, you need something from the M step. M step will give you a temporary estimation of those parameters, and you plug in them into this equation and get a temporary estimation of the posterior of Z. After you get the estimation of PZX, you plug in this guy into the lower bound. And what is the lower bound? It is a function defined over all the global parameters. Let's try it. So the lower bound is EQ log Pxz minus EQ log Qz. So we plug in Q equals to Px given Z into this guy. Z Px Pz given X log Pxz minus the second term can be eliminated because Pz given X is some quantity, some numbers you already computed from the E step. So here, this guy is a constant, so you can drop it out. And for the first one, so So this becomes z p z given x. This guy is log px given z pz. Use the product rule to factorize the joint distribution. And the second term is some constant. We plug in the possible values of k. So it's from k from small k from 1 to capital K, p z equals to small k x log px small k plus some const. In the following steps, I'm going to drop this const. So it becomes this guy is multivariate Gaussian, so it's log 2 pi sigma k transpose. This is the first term, and plus the second term. Second term is pi k, so it's log pi k. And the d here is the dimension of the dimensionality of your data points. So you can see that this lower bound is a function defined over all the parameters. It's 2 pi here. And this guy here is some numbers you estimated from the E step. So you can think of them as numbers. So this function is defined over sigma k, mu k, and pi k. And now you can use whatever methods you like to optimize this lower bound. Basically, we take the derivative of this function with respect to those parameters and send the derivative to 0 and get our update. Let's try a simple one. We use L denote this function. We take its derivative over mu k. Mu k is the mean vector of is the center of cluster K. So the derivative becomes pz equals to kx, and the only term in one mu k is this guy. So it's over 2 and sigma k inverse x minus mu k, and it's 1. And send it to 0. So we get an update of mu k as here. I mentioned earlier, for simplicity, I just use one single point to do the learning. Actually, in practice, we will have central points. So you can plug in this product all the way down to here. There will be a sum I equals to 1 to capital N, and all the x will become xi, xi. So we take the derivative of this function with mu k, and here is n, a sum over all the points. Here, xi. And the update over all the points, pz equals to there. They should also binded to xi, because z is a local variable of xi. Zi equals to k xi multiply xi and over and we get our update of mu k. And similarly, we can do the same for sigma k and pi k and get our update of the parameters. Remember that pi k, mu k, and sigma k are called global parameters. So this is basically what we are doing in the M step. And after the M step, we get our estimation of the global parameters and plug in the parameters into the E step and get another new update, a new estimation of the PZ given X. And you keep doing this until convergence. Any questions here? Okay. Not here. This function is a non-convex function. The EM algorithm can only convert to a local optimal. I won't do it here. It takes a lot of time. Yes, sure. This is just an example. You should also do the similar things for sigma k and pi k.
Is that term just the determinant of the covariance matrix?
Yes, it's a determinant.
Which term is determinant?
Log determinant sigma k. Yeah. So let's have a summary of the EM algorithm. We start from here. We want to do the parameter estimation using MLE, but it's very hard. So we play some tricks here, and we introduce this latent variable z. And we do a trick here and get our expectation like this. And we use Jason's inequality to get a lower bound of the log likelihood. And we also notice that because Q there is arbitrary, you can choose whatever distribution you like. Also, derivation follows naturally. But if you choose QZ and PZ given X, this lower bound will equal the original log likelihood. So you can operate on this lower bound, which will give you the exactly solution as you do with original log likelihood. So how can we do this? We use two steps, which gives us the EM algorithm. And in the E step, we estimate this probability. And in the M step, we plug in this guy into the lower bound and estimate the global parameters. And when we have global parameters, we plug in them into this step. Because to compute PZ given X, you need the global parameters. And you keep doing this until convergence. Why it's called EM? Because in this step, there is a multinomial distribution. And we know that the expectation of a multinomial is the same as this distribution. This is expectation estimation per step. And in the second step, this M step, we are trying to maximize this lower bound, which is equivalent to maximize the original likelihood. So that's why it is called EM. So in the E step, you can see that what we are doing here is to estimate this distribution. They can take the value from 1 to capital K. So you do this for all of them. And after this step, plug in this Q PZ given X into the lower bound and do the maximization. You may wonder, there is something non-trivial here, that is how to estimate this covariance matrix. look at this lower bound. The terms involve sigma k is log determinant of sigma k. And here you have a sigma k inverse. So if you take the derivative with respect to sigma k, actually I don't know how to do the derivative with respect to sigma k of this term. So what we can do is